Dear students, now we are going to discuss the basic types of feedback topologies in detail. Before going to discuss the feedback topologies, let's discuss the types of amplifiers. Based on the quantity to be amplified, it can be either voltage or current, and the desired form of output. The amplifiers can be classified into four types. The first one is voltage amplifier. So in this one, the output voltage is directly proportional to that input voltage. That means input and output both are voltages. So here the proportionality constant or gain of that amplifier is AV is equal to output voltage by input voltage. The next one is current amplifier. So in this one, the output amplified current is directly proportional to this input current. Here the gain is AI is equal to output current by input current. The third one is Transconductance Amplifier. Here that output current is directly proportional to the input voltage. So input is voltage, output is current. Here the proportionality constant is represented as GM, that is transconductance or mutual conductance. That is the ratio of output current to input voltage. The last one is Transresistance Amplifier. Here the output voltage is directly proportional to that input current. Here the proportionality constant is represented as Rm, that is equal to V0 by II. So before going to discuss feedback topologies, let's discuss very important concepts called sampling type and mixing type. Based on the type of sampling at the output side, that can be either voltage or current, and type of mixing at the input side, we can classify the feedback connection into four types. This is the basic feedback amplifier circuit. So we are going to give the input, we are going to get the output, and we are giving that feedback signal through this feedback network. So taking the portion of the output is known as sampling network, and then mixing that feedback signal with this input is known as mixing network. So these two are very important. Sampling can be done based on the output signal, voltage or current. Mixing can be done either series or shunt. Okay. So here sampling network at the output side. If you are going to take the samples of that output voltage signal, we can use shunt connection, that is parallel. Okay. If you are going to take current as a sample from the output side, we can select series connection. So you have to remember this: voltage at the output side means shunt, current means series. Then the mixing network, if you are going to connect the feedback signal with the input side, we can use two types. One is shunt mixing, another one is series mixing. Okay. Next one is four basic types of feedback topology. The first one is voltage series feedback topology. Here the first term voltage represents the sampling process at the output side. So we are going to take the samples of this voltage and provides that feedback signal in series to the input side. So it is called as voltage sampling series mixing feedback topology. It can also be represented as series shunt feedback. So this series represents the mixing at the input side. So we can write the series as first one, and here voltage is always represented by shunt connection. So we can say series shunt feedback. The next one is current series feedback topology, and connect that feedback in series with the input side. That is called as current series feedback topology. It can also be represented as series topology. So here mixing, input side is series, output side is current. Current can be represented as series connection. Okay. You have to remember this: voltage means shunt, current means series. So next one is current shunt feedback topology. So we are going to take the current samples at the output side and connect the feedback signal in shunt connection with the input side. So here it can also be represented as shunt series feedback. The last one is voltage shunt feedback topology. It is represented as shunt feedback. So shunt is here, voltage is represented as shunt. Okay, do you all understand? So this very important in feedback topology. Let's discuss each type of amplifier with its feedback topology. The first one is voltage amplifier. It is an amplifier which provides an output voltage in directly proportion to the input voltage. That means V0 is directly proportional to Vi. We can use the proportionality constant, that is nothing but the gain of this voltage amplifier AV. That is equal to V0 by Vi. Here the input is a voltage signal, output is also a voltage signal. Since it is a voltage source, we can use Thevenin's equivalent circuit. This is a general diagram of this voltage amplifier. Voltage source in series with this resistance. That is Thevenin's equivalent circuit. Here it is that amplifier, and we can have the load resistance. Across that we can get this output voltage. Thevenin's equivalent circuit of voltage amplifier is given here. The voltage source in series with the source impedance or source resistance. This is the input side, and here the amplifier can be represented in terms of small signal equivalent circuit. Ri represents the input impedance of this amplifier. Ro represents the output impedance of this amplifier. Here we are going to get the amplified output voltage signal. Since it is a voltage signal, we can have that voltage source with that gain AV. Okay, so here the output is AV multiplied with this input signal Vi. Then the load resistance, across that we can get the output signal. So here amplifier is represented in terms of internal components Ri, Ro, AV into Vi. For this voltage amplifier, the condition is this input resistance should always be high when compared with this source resistance. Similarly, the output impedance should be low when compared with this load resistance. So whenever these two conditions are satisfied, we can get the high stability and the maximum output. Do you all understand? So that is the condition of this voltage amplifier. The input impedance Ri should be high and output impedance should be low. For an ideal case, this Ri can be an infinite value or Ro can be a zero value. In order to achieve this condition, we can select a proper feedback topology to achieve this condition. A suitable topology for the voltage amplifier is the voltage sampling series mixing topology. That means voltage series topology. So here you have to remember, for this voltage amplifier, the feedback topology is voltage sampling series mixing topology. So this topology is used to provide the high input impedance and low output impedance for this voltage amplifier. So this is the voltage series feedback topology for this voltage amplifier. Here we can have the input source signal along with this basic voltage amplifier with the load. So here we are going to take voltage sampling. Voltage means what? Shunt connection. Okay, and this side the mixing is done with the series connection. So series means this is a series connection here. Do you all understand this one? So this connection is also known as series shunt feedback because input side is series, output side is shunt. This feedback topology provides high stability for this voltage amplifier, high input impedance and low output impedance. High input impedance means RIF is equal to Ri is nothing but the input impedance of this voltage amplifier that has to be increased by the factor 1 plus AV beta. Output impedance, that is ROF, with this feedback we can decrease its value. This RO is the amplifier output impedance that can be decreased by using this feedback with a factor 1 plus AB beta. Next one is current amplifier. It is an amplifier which amplifies the input current signal and provides the output current signal. So here the output current is directly proportional to the input current signal. That is IO is directly proportional to II. Then we can use this proportionality constant, that is nothing but the gain of this amplifier AI is equal to output current by input current. Okay, here both input and output are current signals. So input signal is a current source. We are going to use Norton's equivalent circuit for this amplifier. So this is the small signal equivalent circuit of this current amplifier. We are using the Norton's equivalent circuit for this current source. So IS in parallel with this source resistance, that is called as Norton circuit. Current source in parallel with the resistance is the Norton circuit. The amplifier can be represented as Ri, that is the input impedance of this amplifier, and this Ro is the output impedance of this amplifier. We are going to get the amplified current output signal. Then we can use AI, II. Here AI is the gain of this amplifier. Do you all understand this? So since we are using this current signal at the output side of this amplifier, we can use Norton circuit in this one. So this current source in parallel with this output resistance and then the load resistance. This amplifier, we are going to get the current through this resistance. Okay. So here the output current is IL, input current is II. Do you all understand this? For this current amplifier, the important condition is the input resistance or input impedance should be low and the output resistance should be high. For an ideal current amplifier, the input impedance is 0, output impedance is infinite. In order to satisfy the condition of current amplifier, that is low input impedance, high output impedance, we can select current sampling shunt mixing feedback topology. That means we are going to take the samples of output current and provide that feedback in shunt connection at the input side. That is also called as shunt series feedback topology. So this is the diagrammatic representation of current sampling shunt mixing topology. So here that input is current signal. So it can be represented using Norton's equivalent circuit, that is IS in parallel with RS. This is simple current amplifier. We are going to decrease the input impedance of this amplifier and increase its output impedance by using this feedback connection. So here the output is IO that can be sampled for this feedback network and we can get IF, that is the feedback signal to this current amplifier, that is equal to beta into I naught. Do you all understand this circuit? So here current sampling means current series sampling and here we are going to provide shunt mixing. It provides high stability and low distortion, low input impedance, that is RIF. Input impedance with this feedback is equal to Ri by 1 plus Ai beta. This current amplifier is having its own value Ri that can be reduced by the factor 1 plus Ai beta due to negative feedback. Okay. High output impedance, that is ROF is equal to RO into 1 plus Ai beta. So the output impedance of this amplifier is increased by the factor 1 plus Ai beta. Next one is Transconductance Amplifier. It is an amplifier which provides an output current signal in direct proportional to the input voltage. That means input is voltage, output is current. The output current is directly proportional to the input voltage. Then we can have the proportionality constant as Gm. That is nothing but the ratio of output current to input voltage. It is represented as short circuit transfer conductance or short circuit mutual conductance. Okay. This is the small signal equivalent circuit for this transconductance amplifier. Here we are going to give the input as voltage signal. So we can use Thevenin circuit Vs in series with this source resistance. This amplifier can be represented as the input resistance or input impedance Ri. The output of this amplifier is current, correct? Input is voltage, output is current. So we can use this Norton circuit. The current source in parallel with this output resistance. Here we can multiply this input voltage with this transconductance value. The output is the IO, that is current, and then the load resistance R. The condition for this transconductance amplifier is that the input impedance and the output impedance both should be high. Okay, it should be greater than this RS. Here RO is greater than this RL. For an ideal transconductance, this Ri and RO both are infinite one. That means very high value. In order to satisfy this condition, we can select a proper feedback topology for this amplifier. Here a suitable topology is current sampling series mixing topology. It is also called as series, current means series feedback topology. So this topology can provide high input impedance as well as high output impedance. This is the current sampling series mixing feedback topology for transconductance amplifier, that is also called as series topology. Here the input is voltage signal, so we can use Thevenin circuit Vs in series with this Rs. Then the transconductance amplifier, it is a basic type of amplifier, and then the load resistor. Okay, so input is Vi, the output is IO, that is current signal. We are going to sample this current signal at the output side. So we can use current means series. Okay, then we can connect this feedback signal Vf, that is equal to beta into I naught, in series with this input side. Hence it is called as series topology. So this topology provides high input impedance and high output impedance which are required for this transconductance amplifier. So high input impedance means RIF is equal to Ri into 1 plus Gm beta. High output impedance ROF is equal to RO into 1 plus Gm beta. The last one is Transresistance Amplifier. It is an amplifier which provides an output voltage signal indirectly proportional to the input current signal. So here the input is current, output is voltage. So the output voltage is directly proportional to input current. Here the proportionality constant is Rm. That is equal to the ratio of output voltage to input current. This Rm is represented as the open circuit mutual resistance or transfer resistance. This is the equivalent circuit of transresistance amplifier. Here the input is current signal. So we can use Norton's equivalent circuit. The current source in parallel with the source impedance. Okay. And then that amplifier can be represented as the input impedance Ri, output impedance as R0. Here the output is voltage signal. So we can use Thevenin circuit, that is RMA, that is the output from this amplifier in series with this R0. Do you all understand this? Input is current, output is voltage. Then we can have RL. Condition for this transresistant amplifier is that input impedance as well as the output impedance both should be low. The Ri is far less than Rs, Ro is far less than this RL. For an ideal transresistance amplifier, both the values should be 0. It is for an ideal case, but practically it should be low. Okay. A suitable topology for this transresistance amplifier is voltage sampling, shunt mixing feedback. So voltage sampling and shunt mixing feedback can provide low input impedance and low output impedance for this amplifier. So here this is the shunt feedback topology. Norton circuit IS in parallel with RS. Then we can give the input current II to this basic transresistance amplifier. Then we can have the load resistance. Okay. we are going to sample the voltage signal because the output is a voltage signal here. For that we can use shunt connection and the feedback is given in parallel form, that is called as shunt. Okay, shunt feedback topology is used to provide low input impedance and low output impedance. So here RIF is equal to RI by 1 plus RM beta, ROF is equal to RO by 1 plus RM beta.